So hello everybody to another meeting of the One World Game Theory seminar. We are happy to have today Phil Reny from the University of Chicago. Phil contributed to many areas in game theory, to games with discontinuous payoffs, to auctions, stable matching, and general equilibrium theory, to name but a few. And today we'll hear another work of Phil. So Phil, the stage is yours.
Terrific. Thank you, Ilon and Galit, for inviting me. It's really a pleasure to be speaking to you all. So yes, today I want to talk about efficient matching in the school choice problem. Most of us, if not all of us, are very familiar with this problem in general. Just a brief introduction. School choice is very common, actually, not uncommon, certainly in the US. Many large cities, public schools, districts within those cities use some method for matching students to schools, and the students are given choice to go to a school that's not in the local area where they live. And these systems are centrally run, and students submit their preferences, that is a ranking of the schools that they would like to attend, from most preferred to least preferred. But of course, it's going to happen that some schools are going to be over demanded, and so not all students are going to have are going to be able to obtain their first choice. There just aren't enough seats at those schools, and so priority rules are set either by the district or the city or the state in some cases to help resolve conflicts between students at any particular school. And very typically, the priority rules are as follows. Let's see, I must be able to point here. Let's see. Okay, so here is a typical list of priority rules. If you have if you're a student, so you should imagine that in the US, grades, elementary school, grades say 1 to 8. And then you typically, high school, after grade 8, grade 9 is you're a freshman at high school. And so usually you change schools. And so you should imagine that you're just graduated from grade 8, and you have to choose now a high school to attend. Let's think of it that way. And it could be that you have a brother or a sister who's attending your first choice high school. Maybe you have a brother or sister who's attending that high school, and perhaps you're in what's called the walk zone. So it's a small distance away from the school. If both of those things are true, then you're in the first priority group of that particular high school. You'd be in the second priority group if you only have a brother or sister there, but you're not in the walk zone. You'd be in the third priority group if you are only in the walk zone, but don't have a brother or sister there. And the fourth priority group is everybody else. If you neither have a brother or sister, nor are you in that school's walk zone. And now these, of course, they're going to be, these are going to generate equivalence classes between students. There could be many students who have both a sibling and are in the walk zone, for example, and there's certainly going to be lots of students at this high school who neither have a sibling there or are not in the walk zone. So they're in the fourth group. And so to establish priorities within these equivalence classes, typically random numbers are also assigned to students. So each student is assigned a random number, and those random numbers are used to break ties within these equivalence classes. And so here's the situation quite generally. So schools have priorities, and we're not going to be thinking about these as preferences. These are just rules that are used to break ties between students. And by the way, if you have questions, I encourage you to just jump in and stop me and just ask your question. If I find there are too many questions, then I'll say so. Okay. The important thing about priorities for this talk is that they're known. So these rules are common knowledge in practice between parents know them well and schools publicize them. So they're not strategic. I mean, they're set, they're known, and there's no changing them. And of course, a student can have high priority at one school, but low priority at another. So while it's true that these priority rules are the rules are the same for all the schools, each student might have a different priority between one school and another.
אני באמצע הסמינר, אני יכול לחזור אליך, מה?
Bob, I love Israel, but you're going to have to speak in English. I'm sorry. If that was a question to me, then I'll need it in English. But
no, Phil, it wasn't a question, so you can go on.
Okay, sorry. Let's see. So, of course, students can have look. I might have a brother at a school, at one school, and I might have no sibling and not be in a walk zone at another school. So I have higher priority, relatively high priority at the first school and low priority at the other. And as I said, random numbers are assigned to break ties within these priority classes. And so after, once we take into account the random numbers and tie breaking, those rules, each school in practice has a strict priority ranking over all the students. So when you take into account the priority rules themselves, and then within those equivalence classes, you use the students' randomly assigned numbers, then there will be a strict priority ranking. Each school will be able to strictly rank all the students in terms of their priorities. And so for the rest of this talk, I'm simply going to assume these particular priority rules are typically used in practice, but they're not going to matter for my talk. All that matters for my talk is that each school can strictly rank all the students, has a strict priority ranking of the students. And I'm going to assume
Phil, is there a mathematical difference between priorities and preferences?
No, there's no mathematical difference. There's strict rankings on the other side of the market.
Okay, thank you.
Thanks, Bob. But in terms of some of the analysis later on, and in fact, momentarily, I'll be talking about Pareto efficiency. And when I speak about Pareto efficiency, it will always be with respect to the student's preferences. So this is where I'm treating the school priority rules not as preferences for the schools. When I speak about Pareto efficiency, it's always with respect to the students only. Okay. So what's a matching? A matching, so let's see, here we are. Here, a matching assigns each student to a school so that no school is assigned more students than it has seats. And the number of seats that a school has is called its quota. A matching violates the student's priority, so say student I's priority, if a school that I prefers to the one that she's matched to has an empty seat, so is not at its quota, then your priority would be violated. Or that school that student I prefers is assigned a student that has lower priority than student I at that school. Okay, so there's two ways for a student's priority to be violated at a matching. If there's a school that I prefer that has an empty seat, my priority is violated. And if there is a school that I prefer at which is sitting a student who has lower priority than me at that school, then my priority is violated at that school. Okay. we'll say that a matching is stable if it does not violate any student's priority. And so this is just the usual definition of stable matching. As Bob said, if we were to think of the school's priorities as preferences, rankings, then it's exactly a stable matching as defined in Gale and Shapley. And of course, we're all familiar with it, but it never ceases to be amazing that a stable matching always exists. It's really kind of a remarkable fact. And more than that, there's a stable matching.
What about the school's priorities? If I recall the Gale-Shapley definition, it refers to both partners, not only to the student.
Good. So let's take
we have the marriage problem, okay? So both the man and the woman are treated symmetrically. Why is it obvious that the way it's defined over here is the same? If you tell me it's obvious, I'll accept it.
Well, I don't want to just say it's obvious. It's true. Let's just talk about the men and the marriage model, and let's talk about that for a moment. And I'm imagining that the women, I'm calling their preferences over men, I'm calling them priorities. Okay, they rank the men. The women, I'm just saying the women have priority rankings over the men. But we can, Gale and Shapley, we call those preferences. When I say I'm doing this, it's not really me. It's the literature, and it's okay. I mean, I think it's the right thing for the literature to do, and so I'm continuing in that good tradition of this literature to talk about these as priority rules. But here the analogy would be that the women have priority rankings over the men have preferences over the women. And to say that a man's priority is violated in a matching, what does it mean? It means that there's a woman that he prefers who ranks and either she's unmarried, unmatched, so that would violate. And by the way, in these, there's an implicit assumption here that all of the schools prefer any student to an empty seat. So that would be that this woman prefers this man to being unmarried. So if she's unmarried and this man prefers her, that would not be stable in the Gale-Shapley sense. That's one way for this man's priority to be violated. Another way for this man's priority to be violated, if there's a woman he prefers and she's married, but she ranks him, he has priority over the man to whom she's married. In other words, she ranks him higher than the man she's married to. Again, that would violate stability in the Gale-Shapley sense. So they're exactly the same, Bob.
But where does it say here that she ranks him higher?
Say again?
Where does it say here that the school, where is it required that
right here.
In other words, one word is assigned that has, okay.
Is assigned a student that has lower priority than I. In other words,
okay, got it. It's over there. Part of the definition of stability is in that previous bullet. Okay, thank you.
Correct. Exactly, right there, Bob. Okay, thanks for letting me clarify that. So, yes, the remarkable thing, of course, that we all know very well, but still amazing, is that a stable matching always exists. Moreover, there's a student optimal stable matching. I mean, that is, there's a stable matching that all of the students, all of them agree is at least as good as every other stable matching. So there's no disagreement when it comes among the students when they are ranking stable matchings. There's one that's best. Okay. Well, so what's the problem? The problem is that this student optimal stable matching, the one that all of the students agree is best, is not always Pareto efficient. In fact, it's typically not Pareto efficient. And it can be really quite bad, at least in theory. It can be the case that all students, the student optimal stable matching, it can happen that all students are assigned either to their worst or second worst school. Okay, so for any number of schools, there are students and preferences and priority orders and quotas for the schools that would have this effect. And I think for any number of schools, any number of students, I should say, there are priority orders for the schools, preferences for the students, where this would be the outcome, that the students would be assigned to their worst or second worst school. And Kesten, a very nice paper in 2010. This is just one of the many things that he does in this paper. And I'll talk more about Kesten's paper shortly. So now you might ask, okay, theoretically it can be quite bad. What about in practice?
Wait a minute, Phil. If I can ask another question, I'm being obstreperous here, but does this happen in the marriage problem also?
Yes, Bob. Yes, Bob. It does. It can happen in the marriage problem.
Okay.
The marriage problem and the school choice problem are really isomorphic.
Same.
Yeah. You can always think about the schools. You can think about each seat as being its own school.
Yeah,
really.
Yeah.
And so it becomes a marriage problem. So is this a problem in practice? Well, it is. Maybe not to this extent, but here's an example. In New York City, a school district in 2006, 2007, over 4,000 grade 8 students could have been made better off by reassigning them after the student optimal stable match without making any other students worse off. And this is empirical work done by Abdul Kadiroglu, Patak, and Roth in 2009. I think it would be interesting to know, you guys know me, I wish I could do good empirical work, and I wish I had the tenacity and patience to do it, but I never seem to get around to it. I think it would be really interesting to know how widespread this sort of problem is.
Question.
They did a little bit of analysis on this, but I'd like to see more data and just to see. I'm guessing it happens a lot. That would be my guess, but I haven't done the empirical work to say that this sort of thing happens a lot. By the way, let me say this was about 5% of the students who were on the grade 8 students that year. There were about 90,000 roughly grade 8 students in New York City that year who were graduating into high school.
Question.
Bernard?
Yeah, I mean, doesn't this contradict that this is student optimal? I thought there's a partial ordering and this is the maximum in among, I mean, without making any other students worse off. Doesn't that contradict that there's a better one than the...
Very good, thank you. No, because it's just telling us that the student optimal stable match is not Pareto efficient.
But what does student optimal mean? Doesn't it mean that
Good. Student optimal means that among the stable matches, among the set of stable matchings, which is a subset of all of the matchings, okay? So among the stable matchings, the student optimal stable matching is at least as good as any other stable matching for every student.
So making better off at the expense of stability, this blue thing would have...
Perfect.
Yeah.
Perfect. Exactly right. Exactly right. Okay. So let me go back up here. Yes. So what's the problem? The student optimal stable match is not always Pareto efficient. And as Bernard just pointed out, whenever that's the case, it must be that any Pareto efficient matching that you choose is not going to be stable. Cannot be. Okay, because if it's stable, it has to be no better than the student optimal stable match, but then that would contradict that the student optimal stable match is not Pareto efficient. So whenever the student optimal stable match is not Pareto efficient, if what you're looking for is a Pareto efficient match, it's definitely not going to be stable. Okay. So, you know, what's going on here? Let's look at an example. What's happening when the student optimal stable match is not Pareto efficient? Why is this happening? Okay, so here's an example. 3 students. So let's see. 3. So the students are here. Student 1, I1, I2, I3. These are the students. The schools are here, S1, S2, S3. Each school has 1 seat. And here I'm listing the students' preferences. So student 1 ranks school 1 first, school 2 second, school 2 third. Over here, let's say school 2, priority ranking of school 2 is student 1 has highest priority, student 3 second highest, student 2 lowest priority. Okay, that's how to read the tables. We know there's a student optimal stable matching. We could go through the Gale-Shapley algorithm. I don't have time. We're not going to do that. So trust me, this is the student optimal stable match. In fact, it's the unique stable matching. So student 1 is assigned to school 2, student 2 is assigned to school 1, and student 3 is assigned to school 3. That's the unique stable matching, and so it's the student optimal stable matching. Now, but it's not Pareto efficient. You can see students 1 and 2, they're together at schools 1 and 2. Notice if they just switch schools, they'd both be better off. If student 1 were to go instead to school 1 and student 2 were to go instead to school 2, they would be strictly better off. So the red matching is a Pareto improvement over the student optimal stable matching. And so what's the problem? The problem is that this violates student 3's priority. It's student 3. Notice we haven't changed student 3's school at all. She's been made no worse off, but she is stopping us from making this Pareto improvement because her priority is violated. Let's see where. Well, student 3 would prefer to be at school 2 instead of school 3 where she's assigned. So if we look at school 2, I'm sorry, student 2 here is assigned to school 2 in this Pareto improving matching. It's student 2 who's assigned there. So let's look at the priorities of school 2. And indeed, notice that student 3 has priority over student 2 at school 2. So if we go back here, no, so yes, student 3's priority is violated here at school 2 because there's a student at school 2 who has lower priority than student 3. And student 3 prefers school 2 to her assigned school. Okay, so that's the problem. We try to make a Pareto improvement and it's some student, other student not involved in the Pareto improvement whose priority would be violated. And that's preventing the Pareto improvement from being made. Okay? Okay. So, excuse me.
Let me have a quick remark. I'm Tamás Freiner.
Please, yes, hi.
Yes, so my remark is that you can have an example. I just checked that you have 3 schools, 3 students, basically it's a marriage problem. And the student optimal stable matching is so not Pareto optimal that it can happen that each and every student gets a better school than in the matching. Because here you couldn't change the position of one student, but it is even possible that all the students have a better position in the Pareto optimal solution.
I agree.
Okay.
Wait, do I agree? Just a moment. Well, okay. Now I'm gonna. So let's see. Let's say that every student. What do I want to say? Let's see. What do I want to say? At least as good. I want there to be at least as many seats as students. So maybe that's also your example. And then I'm gonna say I disagree. Okay, that's not possible.
I think I have an example with 3 schools and 3 students, but let's do it after.
Sure. No. Well, we'll come to a theorem in a moment.
Oh,
when I come to that, we'll talk again. Okay.
Okay. Okay.
Very good. Thank you. Okay. So a little bit on the, there's a huge literature, of course, on stable matching and school choice problem. There is a sub-literature on the issue of Pareto efficiency, both within, there are issues of sort of constrained Pareto efficiency within the set of stable matchings. Sometimes these random tie-breaking rules, they will affect the final outcome. And if what you only care about is the priority orders and not so much the random numbers, then you can sometimes do better if you insist on a stable matching with respect to the priority orders only. I'm not going to say much about that, but some of these papers talk about those issues. Others of these papers talk about strategic issues. I obviously don't have time to talk about all of these papers, but the ones that I want to focus on today are these three that I'll talk a little bit about. The Kesten one I mentioned a moment ago. Let me say briefly, the main import of the Kesten paper was on this issue of Pareto efficiency. And what did Kesten do? Kesten asked himself, why is it in the Gale Shapley student proposing deferred acceptance algorithm, what is it? What's going on there in the mechanics of the algorithm that leads to a Pareto inefficient outcome? And his answer was the following. What happens is that, let's see, it could happen that at some point in the algorithm, how does the algorithm work? We apply to our favorite school, our most preferred school. Some schools will be over demanded and they're going to fill up their seats up to the point where they have no seats left and reject other students. Any student who's rejected in that first round, then you go to your next favorite school, etc. And now what can happen as the algorithm is progressing, at some point, let's take me, I'm a student. Suppose at some point I apply to a school. Let's suppose the schools only have one seat to make my example easy. I apply to a school that Ilon happens to be sitting at. And it just so happens that I have higher priority at that school. So Ilon is temporarily, in the algorithm, is temporarily assigned to that school. But I now apply as a new applicant, and I have higher priority. So Ilon is rejected, and now I'm now temporarily assigned to that school. So now Ilon in the next round has to go down to his next favorite school. And Ilon, goes to his next favorite school, and maybe Galit was at that school, temporarily assigned, and Ilon might have has higher priority than Galit, so Ilon is taken and Galit is rejected, and it could happen. This goes on and on and on and on. Each student goes to their next favorite school, and let's say and the student who's there may be rejected. And what can happen is that eventually, let's say Bob was rejected at his school, and now Bob's next favorite school is the school that I'm at. And it comes back to me, and Bob applies to the school I'm at temporarily and kicks me out of that school. And so what was the net effect of my applying to Ilon's school and kicking Ilon out in the first place? What's the net effect is that all of those students in that rejection chain are made worse off, and I'm no better off. I end up getting kicked out of that school anyway. So that's what's going on when in the deferred acceptance algorithm, that if we just reversed it, all of those students would be made better off, okay? So that's what Kesten does. He says, look, I'm gonna go do the deferred acceptance algorithm, but whenever one of these people like me, Phil, who caused this rejection chain to occur, and I end up anyway getting kicked out of this school, he calls me an interrupter. Okay, whenever there's someone who he calls an interrupter, he says, I'm going to reverse all those steps and just not allow this interrupter to apply to that school in the first place, and then continue the algorithm. Okay, it's more sophisticated than that. You can't, you have to be clever and careful in the way that you do it. And Kesten was careful and clever. But that's roughly what he does. And he goes through the algorithm that way and ends up with something. And it turns out what he ends up with is something that's Pareto efficient and that Pareto dominates, at least weakly, the student optimal stable match. Okay, so he always ends up with something that is Pareto efficient and that weakly Pareto dominates the student optimal stable match. And of course, whenever it differs from the student optimal stable match, it's not going to be stable itself. But that's Kesten, okay? And you know, of course, he's sort of promoting this particular Pareto efficient matching that he achieves. And okay, let me say a few words about Ehlers and Morrell. Ehlers and Morrell have a beautiful, Tang and Yu I'll get to in a moment. Ehlers and Morrell, what they do, again, they're interested in this problem of Pareto inefficient matchings. What they do is they define a concept that they call legal sets of matchings. So they're actually, they define what is a set valued concept. You should think of something like von Neumann-Morgenstern stable sets. There's a blocking concept. You have a collection here. The collection of items are the set of matchings for Ehlers and Morrell. They have a blocking concept that they introduce. It's sort of natural. I can't go into it. And then they apply to this blocking concept von Neumann and Morgenstern's internal and external stability notions. And so they come up with a set valued solution concept that they call legal sets of matchings. Okay, so legal sets of matchings are matchings, and I know I'm not giving you details to understand really what it is. The point I want to make, though, is that it's a von Neumann-Morgenstern type stable set. So it's set valued. Beautifully, they show that this set of matchings, this legal set, there's a unique such legal set, unique. And it's a lattice. And so it has, and with respect to the partial order defined by the student's preferences. So there's a largest and a smallest such legal matching, and they care about the largest one. So there's a student optimal legal matching, a legal matching that all of the students agree is best. Moreover, it's Pareto efficient. And in fact, it coincides with the matching that Kesten defined through his algorithm. Okay, so it gives a little more, it makes it even more intriguing, this matching that Kesten found, that it also comes out of this Ehlers and Morrell's legal set definition. Okay, I have to now go on to back to my paper, but that's these two papers do, and they're beautifully written papers. I encourage you to take a look at them. And they definitely inspired me to think about this problem. Let me say that a particular aspect of this problem that's super important. I mean, it's a really practical problem, and certainly, and here in the U.S., when it does happen, you know, when there are, by the way, there are other algorithms that are used to match students to schools. And when the outcome is not stable, you know, it's a pretty litigious country. That you know, parents have taken schools to court over these things, and so if their students' priority is violated, you know, parents take this seriously, and some of them will take the school district to court, and that's not good for the schools. And so it's really important, if you're going to promote a Pareto efficient match that's not stable, you need to be able to explain clearly, certainly to parents and possibly to judges, you know, why it is that this student whose priority is violated at a school should not be placed there. You have to be able to explain it in clear language. So I think one of the drawbacks of Kesten's approach was that it's difficult to explain that, you know, student's priority is violated because that's what came out of the algorithm. And we could describe for you how the algorithm works, but other than that, and also I think the Ehlers and Mora, where it's a beautiful theoretical result and paper, but the fact that it's set valued, it's kind of a fixed point of a set valued map, any particular matching, because it's set valued, these matchings are defined relative to themselves. Yes, you have to know what the set is first to know whether or not a matching is in the set, is part of this legal set. And so it's very hard to explain why any particular matching should or shouldn't be legal, because each of them are defined relative to the entire set. Okay. So let's see, I can't see what that says because my banner is blocking it. But anyway, so I'm going to take the view, that these priorities are serious, as I said. And so unless a Pareto improvement is possible, really you should respect the priorities. So that suggests that you really would want the selected matching to weakly Pareto dominate the student optimal stable matching. I'm not taking that as an axiom, but I'm saying that would be an important property if you can achieve it. And you should want to achieve it. And because of that, I'm just going to tell you that there are theorems that say any Pareto efficient mechanism that weakly Pareto dominates the student optimal stable matching mechanism is not going to be strategy proof. Okay, so if one is going to do this, you're giving up on strategy proofness, but I'll come back to that at the end. Okay, toward the end, we'll have a theorem that says something, something about strategic concerns. So bear with me. Okay, so as I said, simplicity here is going to be important in school choice, I think, as a practical matter, because one has to be able to explain in those important cases where the Pareto efficient matching is not stable, why it is that some student, her priority is going to be violated, and you have to explain why she can't be placed at the school where she has higher priority. So we get to a definition finally. I'm going to say that a matching is priority neutral if it's not possible to make any student whose priority is violated better off without violating the priority of some student who is made worse off. Okay, say it again. I'm going to say a matching is priority neutral if it's not possible to make any student whose priority is violated by that matching better off without violating the priority of some student who is made worse off. Okay, let's talk a little bit about the motivation here. Recall, stability actually, captures the idea that students have an absolute right to relief from priority violations, regardless of the effects on other students. So yes, what do I mean by that? If you have a matching that violates a student's priority, it's not stable. And if stability is your solution, then this matching that violates this student's priority is just off the table. It just doesn't satisfy the solution. It's not stable. Implicitly, that's saying that this student has an absolute right to relief from this priority violation. And so you have to put her at this school or do something to relieve her from this priority violation, and no matter what, regardless of the effects on other students. On the other hand, priority neutrality, the thing I just defined, it's meant to capture the idea that yes, students have a right to relief from priority violations, but do not have the right to violate others' priorities without remedy in order to gain such relief. And by without remedy, I mean without making them whole. So you can violate someone else's priority. If you make them better off, that's okay. But you can't violate, in seeking relief from your own priority violation, you can't violate someone else's priority and make them worse off. That's not okay. You don't have the right to do that. Okay, that's priority neutrality. Let's go back to this example.
Bill, I have a question about priority neutrality. Can you tell me a little bit about those being worse off? It doesn't matter how much worse they are off.
You know, I'm taking this, I'm doing what this literature does, and it's just, we have these ordinal rankings, and that's the only information we have. And I agree, it would be really interesting to talk about, you know, cardinal preferences if you want, or something that gives some indication of how much worse off students would be.
Ordinal preferences could also be on the aggregate or something. No, but I see. So you're basically not taking a stance on that.
Yeah. Thanks, Carl. So let's take a look at this example that we had a moment ago. This was an example of a Pareto improvement, the red matching over the green student optimal stable matching. It's a Pareto improvement, but it violates student three's priority. Student three's priority is violated at school 2. But I want to claim actually that this red matching is in fact priority neutral, because and how do I need, what do I need to show? I need to show that it's not possible to make student three's priority is violated. So she has a right to relief from this priority violation, but in seeking that relief, she can't make someone worse off and violate their priority at the same time. So notice that in order to make student 3 better off, she has to be assigned to school 2. And so if we just switch, for example, take student 2, assign student 2 to school 3 down here, switch student 3 to school 2. So that makes student 3 better off. It makes student 2 worse off. And moreover, it violates student 2's priority, because student 2 is now at school 3. She prefers school 1, for example, to her assigned school 3. Who's at school 1 in this new matching? Well, student 1 we haven't changed. He's still at school 1. And notice that student 3 has the highest priority at school 1. So if we try to move student 3 to school 2 just by switching the schools of students 3 and 2, we make student 2 worse off and violate her priority. So we can't do that. And let me just say, in the interest of time, that you can't do anything. You can't rearrange students 1, 2, and 3 to put student 3 at school 2 without violating either student 2's priority or student 1's priority and making them worse off. So in fact, the red matching is not only Pareto efficient, it's priority neutral. Okay, so I'm gonna look for matchings. Of course, I'm looking for Pareto efficient matchings, but I'm looking for those Pareto efficient matchings that are also priority neutral. And I'm gonna call a matching that's both priority neutral and Pareto efficient. I'll call such a matching priority efficient. Okay, let me go quickly just over an example. Here we have 5 students, 5 schools. These are the preferences of this. Each school has 1 seat again. And the ... dots mean that the rankings after this don't matter for the purposes of this example. So here's the student optimal stable matching, which is, in this particular case. Here, this happens to be a Pareto efficient matching. I won't go through it. It's just, it's nothing interesting there to check. It's Pareto efficient. Happens to Pareto dominate the student optimal stable matching. I want to show you, though, that this Pareto efficient matching is not priority neutral. Okay, so not all Pareto efficient matchings are priority neutral. So let's see why. Notice that student 2 here would prefer to be at school 3. She's at school 1 in the circled matching. Yes, the circled purple matching. Student 2 is assigned to school 1, would prefer to be at school 3. So who is at school 3? Student 3 is at school 3. So let's look at school 3's priority ranking. Notice that here's student 3, here's student 2. Indeed, student 2 has priority over student 3 at school 3. So student 2 here, student 2, her priority is violated at school 3 in this Pareto efficient matching, the circled purple one. So in order to show that this circled matching is not priority neutral, it's enough for me to show that I can make student 2 better off. Her priority is violated. I can make her better off without violating the priority of any student who's made worse off. And I claim that this matching does it. Here's a matching I claim. It certainly makes student 2 better off. It makes student 4 better off, and it doesn't affect either student 5 or student 1. The only student who's made worse off is student 3. Student 3 is placed at school 4, and I claim her priority is not violated. Why? Because the only school she prefers is the school she was at before, namely school 3, and now student 2 is there. But we already showed that student 2 over here has priority over student 3 at school 3. So student 3's priority indeed is not violated. So I've made student 2, whose priority was violated by the purple circled matching, better off without violating the priority of any student who was made worse off. That tells me that the circled matching was not priority neutral. And in the interest of time, I think I have about 10 minutes left. I'm just going to tell you that this squared matching happens to be Pareto efficient. And it happens that it's not possible to make any student whose priority is violated better off, and that's only student 5, only her priority is violated, without making any student worse off, violating the priority of a student who's made worse off. So in fact, this red squared matching is also priority neutral, and so it's priority efficient. I know that was fast, and I'm just going to skip through those other slides.
Can I ask a question?
Absolutely, absolutely, yeah.
So I mean, the original one where you swapped. Okay, so you're suggesting this as a good solution, but in the other one, the stable matching, I suspect. I mean, where you had the swap between the first and third student.
Okay, yeah, sure. I'll go back.
You're saying, well, this is something that you no. In the one that keep going. I mean, the one that you had there. I mean,
sorry.
Yeah, this purple one. You said that somebody could sue for this swap because it violates your condition. Now, is that easy to find, or would they need to expose an entire new matching to prove that, or is there some local condition where you could prove? My question is, how complicated is this to verify?
I agree, Bernard. It could. How complicated? Give me a moment. It may not be that answer is I'm not sure at the moment, okay. But I think it may not be that complicated given the structure of this problem with the lattice that's available and the fact that it's easy to compute a priority. It is easy to compute a priority efficient matching, one that's both priority neutral and Pareto efficient. Yeah. Okay, your point is well taken, and it is more complicated for parents to establish that there's a problem. And so, when it comes to practicalities, another practicality that is important is transparency, okay. And all of that. And there's going to be a trade-off here, no question. Thanks.
Thanks. Okay.
This is notation. We don't need this. We don't need this notation. Sorry. So let's just skip it. So I'm just repeating the definition of priority neutrality. That's the first bullet point. The second bullet point, I want you to notice that every stable matching is priority neutral, trivially, because no student's priority is violated. So remember, to check whether a matching is priority neutral, you first have to ask, is it possible to make some student whose priority is violated better off? Well, if no student's priority is violated, there's nothing to check. Okay, so every stable matching is priority neutral. Okay, and priority efficient matching is one that's both priority neutral and Pareto efficient. Theorem: there's a unique priority efficient matching, mu star. So it's exactly one matching that's both priority neutral and Pareto efficient. Moreover, this unique matching, mu star, dominates, that is, weakly Pareto dominates every priority neutral matching. And therefore, mu star dominates every stable matching because every stable matching is priority neutral. So every student agrees that mu star is at least as good as every priority neutral matching and every stable matching. It turns out that the set of priority neutral matchings is a lattice. And in some sense, you know, those who do matching theory are going to say, well, of course, everything's a lattice in matching theory. But in any case, the set of, it's not obvious, but it's true that the set of priority neutral matchings is a lattice.
I have a question. What about those preferences? Because you assume them through this randomization, right?
Yes.
So does this really fit your setting? I thought it would have been nicer to have a result that respects the indifference of the school.
Well, okay, very good. So you're not going to get uniqueness if the schools are indifferent.
Well, but I would think that the concept would be more important to think about something that respects the original situation, which is indifference. You're breaking ties through randomization. You're acting like that is their preference, but not, it's just a randomization. So I'm thinking about how you think about this. Why didn't you just define it? And then if you don't have uniqueness, you have something else. You know?
I think that, so there are several things. You know, what this is saying is that if what you want to do is respect the school's priorities, and if what you want to do is respect only the original priorities and not respect the randomization, then there will be multiple. This isn't going to pin down. This isn't going to pin down a particular Pareto efficient matching. Each random is. Let me put it differently. Each tie-breaking rule will generate a unique priority efficient matching with respect to that tie-breaking rule within the equivalence classes.
Okay.
And you could then talk about that set. And I don't have a way of choosing among the elements of that set. But I will say that you know, all of the theories that do select a Pareto efficient matching rely on this a tie-breaking rule like that. So I'll just say that this is to the extent that priorities are coarse, and to the extent that what we're trying to do is respect priorities. Obviously, the coarser the priorities are, the less there is to respect. And so the more matchings are going to be compatible with you know, respecting coarse priorities. So I just don't have anything, you know, interesting to say about that beyond what I've said.
Okay.
So I'm going to move on. Oh, let's see. I'm going to say one thing because I think it was Bernard who asked a question. Someone had an example. Maybe it wasn't Bernard. Someone had was looking for examples, saying that, you know, you could strictly Pareto dominate the student optimal stable matching. Here's a theorem. This goes back to Galen Sotomayor, and you know, this is important for the, you know, for the theory of priority neutral matchings. This theorem turns out to be important. We're not going to have time to talk about it, why it's important today, but let me just mention this theorem because it relates to the question that was asked earlier. Under demanded school theorem, in the student optimal stable matching, there's at least one school that no student prefers to their own. Okay, so take the student optimum, any matching problem where there are at least as many seats as students. Okay, if there are at least as many seats as students, then it's in the student optimal stable matching, there is always at least one school with the property that no student strictly prefers that school to their own. Now, when that's true, you can kind of see that there's no way in any Pareto improvement, there's no way all of those students have to stay where they are. Any Pareto improvement, because if you try to move any of those students, you're going to have to kick some student out of a school where they were and put them in that school. There just aren't enough seats. So this theorem says that in the student optimal stable matching, there's no matching that strictly Pareto dominates, because there's always at least one school that no student prefers to their own. I'll leave that at that because I want to get to, and we can't talk about this algorithm. The last thing I want to talk about is a strategic property of the mechanism that selects I want to consider the mechanism that selects the priority efficient matching. Okay, so we know there's a unique priority efficient matching for every school choice problem. And so we can talk about the mechanism that selects that unique priority efficient matching. And of course, it's not going to be strategy proof. We talked about that because I've shown you already that the priority efficient matching, weakly Pareto dominates the student optimal stable matching, and they're not identical mechanisms. So it can't be strategy proof. That's a theorem in Abdul Kedaroglu, Patak, and Roth. But even though the priority efficient mechanism is not strategy proof, here's what is true. It turns out, don't read that, it turns out that truth telling is max min optimal. So no matter what the school priorities are, suppose they're known, and when they are in practice, if you're a student and you're worried about what the other students are going to, the other students' rankings are going to be submitted, and you look at the worst case, whatever preference you submit, whether it's the truth or not, you look at what's the worst case, what's the minimum worst school you could be assigned to. If that's what you do, it turns out truth telling is optimal for you. You can't do any better but than to tell the truth if you want to maximize the worst school that you might be assigned to, where the minimization is taken over all of the other students' preferences, submitted preferences. So that's a theorem that I can state that says something about why students might want to tell the truth. And I think we're right about at 9 o'clock, so I'll stop there.
Thank you very much, Phil, for this very interesting and clear talk. Any questions?
I have a question about this last truth telling, if I may. Have you checked minimax regret, which would also maybe be interesting to see how that comes?
Right,
because there's certain pessimism in here, and the counter examples that this can be leads to strange outcomes, and minimax regret can lead also strange outcomes. But it's interesting to see what it is true or not with that.
I agree, Carl. I'll check it out. Let me check it out. By the way, I want to give credit to my young colleague Ben Brooks. It was a conversation with Ben. Ben is working in auction theory and doing a lot of min max min optimal auction design. So he has max min preferences on his mind, and it was he who suggested that I think about this. So I'm thanking Ben for getting me to think about this. So Carl, thanks for that. I'll think about.
It's a very nice result. I like this result. I really like the whole talk. Thank you.
Thanks a lot, Carl. Good to see you.
More questions?
Well, I had another one about the strict preferences. I can go back. You're talking about implementation. How do you imagine to implement priorities that are based on a random draw, and explain this to the parents?
I've already admitted once, I'm happy to say, put it front and center again. I'm not, I don't have the knowledge base that people like Al and his co-authors and I don't know, Utku Unver or Tafun Sanmez do on this school choice problem. They have a vast amount of knowledge. I've read a lot of their papers. And I've just never heard. They do a lot of discussions about practical problems that arise. I've never heard them say that there have been any legal or difficult issues that come up with respect to the randomly assigned numbers. These numbers are assigned to the students. The parents take those numbers seriously, and they're very happy when they get a good draw, and they get a bad draw. It's a bad draw. I mean, they accept it. And
I wouldn't, but then I wasn't in this. Okay, fine, good.
So look, it's a great question, and I don't know really I don't really know the answers to how parents feel about these things.
I guess it's considered fair because, I mean, if there's a limit of resources, how do you, I mean, what else? Everybody could come and say, but I deserve to have a higher number. That doesn't make any sense. So fairness is fair.
Very nice. I agree. I think there's a general feeling that when you're in the equivalence class, we both have a sibling at the school, we're both in the walk zone, the tie has to be broken somehow. Okay. I mean, I wish I won, but I didn't. And anyway.
Do we know that the Pareto efficient allocations without random assignment can be established by randomly assigned tie-breaking rules? Do we know about that? Otherwise, we're missing things. We're missing outcomes. There could be additional outcomes that cannot be generated. They're Pareto efficient, but cannot be generated by this these tie-breaking rules.
It's a good question. I'm going to guess that everything can be. Certainly, if you give me something that's Pareto efficient, and let's see. That's a good question. Actually, no. So let's see. I think what you're saying is it has to weakly Pareto dominate the student optimal stable match. So take something that's Pareto efficient, weakly Pareto dominate student optimal stable match. Could it be the outcome? Could it be priority efficient under some tie-breaking rule? That's the question. Don't know the answer.
Could easily be yes.
I'm guessing the answer is yes. I'm guessing the answer is yes, but could Pareto, wait. No, probably not. No. Because you see, not any Pareto efficient, okay? So it has to at least, it's going to have to respect the course priority order.
Of course, only those. No, of course, that's the idea.
Well, okay, so one has to define something like
that's easy.
Priority efficiency with course priority ordering. So let's suppose we could define that. I'm going to guess if we define that properly, then the answer is going to be yes. It's a guess, but only because you can break ties any way you want and just have the random numbers reflect the way you broke ties. But it's a guess.
Are there additional comments, questions, ideas? Okay, so thank you very much, Phil.
This was great. Thank you. It was a real pleasure speaking to you all. Good to see everybody, and take care.
And see you all in 2 weeks.
Thanks.